Okay, so today my name is Geemi. I'm a fourth-year PhD candidate working with Dr. Andrew White. And today I'm presenting on our work that generates molecular counterfactuals for which are also model agnostic. Okay. Now, before we move on, when I started working on this field a few months ago, last year, I kept hearing the word black box, but I didn't understand what it meant because when we talk about a deep neural network, we already know the functional form of it. So I didn't understand what is it that we don't know because we already know the weights and biases, the parameters in a functional form, right? So although we know these parameters, it actually did give us very little insight into why we make that prediction, why that prediction was made by this given model. So that is where explainable AI comes into play. It helps us to understand what was the reason for this prediction, especially in cases where we have to rely on like the correctness of a prediction or like knowing why a certain prediction was made. For example, like self-driving cars or medicine, it is important that we know that okay, this is why this prediction was made. This was the reason. So now, before we go further into my talk, I would have like to clarify some definitions so that you would know what I mean by this. First of all, interpretability of a model refers to how much we can understand a given prediction, the course of a prediction. And a justification is actually evidence as to why a certain prediction was made. Now, we usually use justifications. We see it often like accuracy of a model or something. Now, that is a justification. Now, next is an explanation. It gives us the information for the context to identify the cause of a prediction. All right, so that's done. Now, I got this from Dr. White's book. It is an online book that is available for everybody. Now, in Explainable AI, we have like two main categories of explanations. First are the self-explaining models, which are like, of course, self-explaining. Now, something that comes under that are the surrogate models, or like a common example that is closer to us chemists would be molecular dynamics simulations. Now, that is a self-explaining model. Then we have the post-hoc explanations. Now, of course, this is an additional task that you have to do because once you have done your training. Post-hoc explanations look at identifying data importance or feature importance. For example, say identifying this feature contributes more towards this prediction than the other features, likewise. And then we have counterfactual explanations, and that is where our work focuses on. Okay. A counterfactual, the definition of a counterfactual is that it is an example as close as possible to the original instance, but with a different outcome. Let's say like somebody telling me like your paper would be better cited if you had a shorter title, right? So something like that. Mathematical, it's like minimizing, a counterfactual has to minimize the distance between the original and itself. Also making sure that the prediction would be different to the original prediction. We use counterfactuals because they're very intuitive to understand. I will, during my talk, you will see why. And these counterfactuals also help us to capture the causal and non-causal relations that exist between the inputs and our outputs. Okay. Now, of course, in our work, we are looking at we are trying to investigate problems in the chemistry domain, and that is where the molecular counterfactuals comes into play. Now, let's say I have a base molecule which lacks activity against a certain property. So that is my base molecule. Now, a counterfactual would be something as close as possible to my initial structure, like this. and it would be, the outcome would be different. So that means the counterfactual has a prediction, a label which is or else an activity that is true, which was positive here. Now, like a counterfactual explanation we can infer from this is that we can use the counterfactuals to say something like the carboxylic group here is an explanation for the lack of activity of this base molecule. Now, that is how we use molecular counterfactuals in our explainable AI domain. Now I'll talk about our method. Our method is called MACE, or Molecular Model Agnostic Counterfactual Explanations. Although counterfactuals are very intuitive to understand, one of the problems with generating counterfactuals is that most of the time it requires optimization over the input features, or it requires training again, or additional data to create these explanations. But the advantage of MACE method is that it requires no gradients, training, or additional data to create the explanations. And most importantly, the key advantage is that our method is model agnostic. That means it doesn't depend on the model architecture. So you can use it for regression tasks, classification tasks, different model like GCNs, RF model, random forest model, likewise. Now, what happens in our method is that first, one of the things I would like to highlight here is that counterfactual explanations are actually local explanations. That means you can, like when you have a base molecule, you can generate counterfactuals for that base molecule. Now, what happens in our method is that we start with a base molecule, and then we generate a chemical space around it first. Now, to generate the chemical space, we use the stoned algorithm that was developed by Akshat Nigam and others at Alan Asperguzik's team. Of course, all of you must know him. And I would like to give a shout out to them for developing this brilliant idea. So we use the stoned algorithm. What stoned algorithm does is that it starts with a molecular representation, and it generates molecules close it like a local chemical space around it through mutations to the initial starting representation. But when you talk about these molecular mutations to a molecular representation or generative models in general, one of the issues that comes with that is that it might lead to generating molecules that are actually invalid. So how we overcome is not us, basically in the stoned algorithm, how it is overcome is using selfies embeddings. Now, selfies again was developed by Mario Kren and others from Alan's group. And these selfies embeddings have this surjective property, which means every mutation leads to a valid molecule. And that is how our method is built. So that we start with a molecule. Let me show you an illustration first. So it would be much better than me explaining everything. So we start with a base molecule, and we use the stoned algorithm to expand the chemical space or generate a local chemical space around the base molecule. And then we identify what are the counterfactuals in our local chemical space. That means the molecules which have high similarity to the base molecule, but with a change in your counterfactual, in your label. So this is the whole idea behind the MACE algorithm. Before I go into results, I would like to talk a little bit about some parameters that we use in our method. First of all, the size of the chemical space, how many data points are there. We use a default value of 3000 and the number of mutations that are allowed on the initial selfies embedding. By default, we use a value of we allow 2 mutations. And to do the mutations that can happen for the base molecule in the stoned algorithm are the deletions of your atoms in the starting structure, or additions or substitutions. Now for substitutions, we can give an alphabet. Currently, we use the alphabet. We use a very restrictive alphabet. By default, it is the base alphabet. We call it the basic alphabet, but of course, a user can give a different alphabet if they may prefer. And then to find one of the key points here is that when we identify a counterfactual, of course, you have to find the similarity between the two data points. That means in this space, or else what is the chemical similarity? And to do that, we use tiny motor similarity of the Morgan fingerprints of the given molecule. And then specifically, it is the ECFP4 fingerprints that we use.
Question.
Yeah.
So are you looking for only one counterfactual or many of them? Because in your previous example, you kind of seem to be looking at only one, but in some application, you can have different groupment that explain the activity of the molecule.
Yes, yes. So you will see in my result, it's not just one counterfactual. Like in this case, I believe those are the yellow points. So all of these are the counterfactuals. And you can like check you in our method, we actually sort out the counterfactuals from the closest to the furthest. So you have that entire list of counterfactuals. So you can use a few or like all of them if you want to infer conclusions, explanations. Does that answer your question?
Yes, but then that raises another question is, what happened when many of those like explanation kind of contradict each other? Like maybe in one counterfactual, you have the carboxylic, in this particular example, the carboxylic groupment is preserved and is the chlorium that's changed. How do you conciliate those things together to generate the explanation of what's causing the activity of the molecule or the inactivity of the molecule?
Okay, so so the counterfactuals gives you an like an explanation as to why this was changed. And again, of course, depending on the different counterfactuals you can get, there might be one molecule might have an addition, or there would be a different deletion or a substitution at a different place of a functional group. But you can use, as chemists, I think that's where our chemical intuition comes into play to make the correct judgment, I would say. But this gives us like a more context into understanding why what is the cause for this prediction. Now also you can, it's like using, let's say, there are different methods like feature attribution methods that you that might like be useful to answer that question, I would say. For example, like which functional group has the highest contribution also. So I would say we can use our chemical intuition also in addition to this to complement our conclusions. Is that clear?
Yeah, that's clear. You have two more questions in the chat.
Okay, let me see. How do we go back? This is from Navav. How do we go back from the point in the chemical space to the structure of the molecule? Oh, okay. So when we generate the counterfactuals, it's because so we have a data point is based. This is just an illustration for visual purposes. But what happens is you have the surface embeddings of the starting structure, and then you just mute it and then you mutate it, and you have the surface embeddings of each and every data point. So it is like I will show you will see it later on. Like each counterfactual has its label, its surface string, small string, and its label with it. So it's very easy to get the structure from data point. Okay, Elena, okay. Does this method consider chirality? Now that is something I would get into a little further into our talk, but it depends on how we measure the similarity when we consider or the representations that we use to represent our molecules? Currently, no, because ECFP4 does not account for Morgan fingerprints do not account for chirality. Okay, I will talk a little bit towards the end about it, but that's a very, very good question. Thank you. Thank you to both Berlin and Nawaf. Okay. Right. All right, now I'm showing some results that we have. In our first example, we have the blood-brain barrier permeation prediction task. Now, this is a classification task that is this is a very classic problem that has been addressed. And in this task, we start with a data set which has labels saying whether if a molecule can permeate the blood-brain barrier or not. And to address this task, we are using a random forest model implemented in scikit-learn. And first, we train our model, and it is comparable to the state-of-the-art methods that's available right now. And in the inputs to our model are the molecular descriptors that we generate with ModeRed. So these are just not super important to the counterfactual generation, but for the machine learning enthusiasts, that's why I added that figure here. Okay, now this is an explanation for the given model, the random forest model. So we have a base molecule, and so in this example, this molecule cannot cross the blood-brain barrier. And then I use the MMACE method and generate counterfactuals. I have shown the first 3 counterfactuals that here, the top 3, and by definition, a counterfactual must, of course, be able to cross the blood-brain barrier. Now, an explanation we can infer by looking at that is that this negative example can be made to cross the blood-brain barrier if the carboxylic group is altered. Now, so this is an explanation. This is an example of an explanation you can infer with the counterfactuals that we have here. Now, the second application I have shown here is a solubility prediction task. Now, this is a regression task. So we have to change our definition of a counterfactual, because initially, if it's a binary classification task, a counterfactual by definition would have a flip in your label. But in this case, we have to consider a change in your prediction by a certain magnitude. Now, in this case, we are using an RNN model implemented in Keras to predict the solubilities, and that's the model that we are using. The change in the magnitude of the solubilities in our paper, that we use a value of 1, and of course, this is a hyperparameter that is specific to the users. This is the architecture of the model, and we have a good fit in this parity plot, you can see. But now let's take a look at some explanations. Now here I'm starting with the base molecule, and we ask the MMACE method to generate counterfactuals for us. And one of the implementations in our MMACE algorithm, or like in our software package, which I will talk in later slides, is that you can visualize where each counterfactual is with respect to the base model in a local chemical space. So we have a few counterfactuals, like top 4 counterfactuals, let's say. The closest counterfactual has a similarity of 0.85, and the decrease in solubility is 1. And then you can see in this case, or like here, like this molecule, this counterfactual has a similarity of 0.82, but the solubility has increased by a magnitude of 1. I have some questions. All right. Chen has asked, will we have access to? Okay, never mind. Right. Okay. Yeah, so an explanation we can generate, like infer from this is that by looking at this for top 4 counterfactual is that hydrogen bond acceptors or the alkane chain lengths are contributing reasons for the solubility of this base molecule. Now, again, something I would like to highlight here is that this is why I think this is a reason why counterfactuals are useful, because you don't need to have like expert knowledge to understand, to interpret the results, because by looking at these small changes, you can come to you can generate an explanation. That is why I believe counterfactual explanations have has a broad range of applications. Okay, in third example, this is an HIV inhibiting activity prediction task. Again, this is a binary classification task that we have implemented, that we are trying to address with a graph convolutional network. And here we have the inputs to the GCN are SMILE strings, and then of course details of the graph convolutional network, and then you get predictions. We have trained it with the data set that we got from the Kaggle competition. And now in this task, we have this an explanation. An example here would be, we have this base molecule, which is positive towards inhibiting the HIV activity. And my counterfactuals would then have a flip in the label. So it would be negative towards inhibiting the activity of HIV. And something that we can see here, like an explanation, is the terminal diamide group has a significant contribution to the HIV inhibition activity of the base molecule. So I think Prudence, you asked this question, if it is just one counterfactual or many, you can actually look at many counterfactuals if you want to come to generate a profound conclusion. I think I have a question. Okay. We have Lance. Since the method looks for the most similar molecules in a database, I guess the performance of this method is reliant on the choice of the database. Actually, the stoned, yes, Cass has answered it. The stoned method doesn't it's not looking at a data set. So in the stoned algorithm, what happens is that you start with the starting string representation, and then you mutate the starting representation so that you will come up with different, like you will generate different molecules around it in that around the given space. So, but yes, I will get that in a little bit. Yes, it can be dependent on the data set if you use it instead of the stoned algorithm. Yes, that's true. This is just, yeah.
We do have Emmanuel who is raising his hand.
Oh, okay. Yes, Emmanuel.
I have a quick question about the embedding of counterfactuals. So let's say that I train my model with a molecular descriptor or a GNN, for example, but the counterfactual, the similarity between the molecules are computed using ECFP4. So how, I'm not sure if it properly reflects what the model is actually looking at, because the embedding space are not the same. So how do you deal with the fact that what you're observing with the counterfactual might not be what the model is focusing on to make its prediction?
Oh, I got it. So you're asking, like, if you have a model, like, will the representation of the model affect the usage during the usage of the algorithm, the MMACE algorithm, right? Okay.
Yes, because you are looking at different representation.
Right. So now that implementation part is in the MMACE algorithm. So for example, I have a GCN model. It takes in SMILES as its input, and the output would be whatever I'm trying to predict. But when you give your model into the MMACE algorithm, what MMACE algorithm does is that First, it would create the chemical space. That means it would have a list of selfish strings which would be your chemical space basically. And those selfish embeddings would then be converted into smiles and given to your model to get the labels for each counterfactual or each data point in your chemical space. So for that part, you don't need to worry about any representation problems. And once you have got the labels or whatever, you can once you have the chemical space, then you can what happens is that then we can identify if that given molecule is a counterfactual or not. And that is where the the ECFP4 comes into play. So once you have the selfish embeddings in your chemical space, our method, it would generate the molecular fingerprints and then measure the Tanimoto similarity to identify and also get the labels from the model and identify if it is a counterfactual or not. Does that answer? Was I clear?
My question was more about the what the representation, the embedding that the model is looking at versus the one that you're using to make the counterfactual. So to give an example, you can have two molecules that have very high Tanimoto similarity looking at ECFP4, but from the model perspective, they are very different because the representation that you're using to build your predictive model is separating them. As the a similar example would be to have molecules that are very different in terms of structural similarity, CFP4, but for the representation that you're using to build your model, they look quite similar because you're using some form of molecular descriptor. So how do you align this disparity with the counterfactual explanation that you're making?
Oh, I think I understand. So it is like you're asking if how do you compare the similarities between the descriptors that you use in the model and the ECFP4, right? Is that correct?
Yeah, so like basically, does the model support changing, like have you experiment with using the same representation that you use, for example, to build a predictive model? So when you computed, you build your model using moderate descriptor. So did you use those descriptor to build your the embedding space? Because that might be a bit more relevant than the ECFP4.
Yes, there are in the exmol package also you can use different types of descriptors other than ECFP4, but something that I want to highlight here is that how we measure similarity. Yes, of course, it is a determinant factor in identifying a counterfactual, and you might use a different molecular representation to get your results in your model. But here in this case, what we are trying to do, how we align here is that it shouldn't matter to get the prediction, because the ultimate idea is that you have different molecules, and what we do is that we have after we generate the chemical space, right, we can use that chemicals the string representations or whatever you use in your model to get the predictions from your model. So you already know how your model treats that given molecule, right? So that is what's important to you as a chemist. But the counterfactual generation part is where we use how we identify it as whether it's a counterfactual or not, is where we use the moderate fingerprints. So I think if I'm using a model, I would just be more mindful about what my prediction says, not about the metric of similarity which we use is just to identify, is for the definition of a counterfactual. So would that be, is that clear?
Yeah, thanks.
Okay. So I think I have some questions.
Maybe one more question. So for example, on the previous slide, we have a model with a rock IUC of 0.7. So
Sorry,
there
I'm
is
sorry, I
some.
didn't hear.
So in the previous slide, yeah, here we have no, not this one, the next one.
Next one.
I'm not sure.
This one?
Yeah, this one. Yeah, thank you. So yeah, the IUC of the model is 0.8 approximately, and so the prediction of there's some error with the model itself. Then we are
Yes.
using this same model to actually identify the counterfactual. So basically, when I'm actually maximize, so my constraint might not be exact. So the yeah, my constraint f of s and different of s of my counterfactual is not actually always true, right? The error code giving that is not always true. So I'm wondering if there's anything we can actually do to change that, because if the model is not reliable, then there's no, yeah, the counterfactual are even more less reliable, right? So
yes. So what this algorithm does is that it generates explanations for your model. So if I have a model, it generates explanation for that specific model, right? So yes, of course, we have to make sure that our model is actually correct, first of all, to generate explanations, like to generate any prediction. Otherwise, the application would be incorrect. Yes, that's true. So I think it comes from the user side, like what is the accuracy of your model? It's not the MACE algorithms work to actually account for the incorrectnesses in the model itself. Does that answer?
yeah, definitely. I think I was maybe thinking that maybe identify counterfactual using the example in the training set might be not a better, but like another alternative to circumvent the problem when we don't have a very accurate model, because we do know that in molecular modeling, like many things can contribute to accuracy, and sometimes it's very difficult to have a model with high accuracy. So yeah, maybe
yeah, that's
using
correct.
the
That's
training
true.
set might be better.
Yeah, if the counterfactual itself is in a is in the training data set, of course you can expect a better result because the model has already seen it. But if we differ further from the training data set, then it can lead to an incorrect prediction. That's true. Emmanuel has a question. No, okay, right.
Oh, sorry.
Okay. Now let me talk a little bit about what are the effects of the parameters that we have used in the MACE algorithm and how it affects the predictions, the counterfactual explanations. First of all, when I said in our paper, the results contained up to 2 mutations, but in the Stone algorithm, it is the number of mutations in the Stone algorithm that we use. So as you can, like the Stone algorithm randomly picks the mutations. So what we can, it's somewhat obvious that it's expected that when the number of mutations allowed on the base molecule, the starting point is high, you move further and further from your local chemical space. And when you have less number of mutations, it generates a chemical, like it is more within the borders of your local chemical space. So that is why we picked a value of by default we allow up to 2 mutations, but of course we recommend 1 to 3 is a good fit. But if you want to expand or like investigate further, I think a higher number of mutations is also preferred, but is fine. Not fine, but it's up to the users. And then, yes. And then the number of the alphabet that we used, or we allow, we use in the Stone algorithm. That also plays a very important role because, for example, now in this case, I am starting with this base molecule and I the three counterfactuals here I've shown are the top counterfactual from three different sets of alphabets. The first one is the default method, and then we have the alphabet that comes from the training data set rather than the restrictive case that is by default here. And then the third case is the alphabet that is by default is in the self is in their code. So something here is that this is again user specific, but by using a more restrictive alphabet, of course, you can generate counterfactuals that might be chemically, like not the validity, but the chemical stability, and those concepts, you might have to be mindful about that also when you expand the allowed mutations or the alphabet in this case. So, like if, for example, if you take this first counterfactual and the last counterfactual, the similarity is basically the same to the base molecule, but this is a radical here. So as a chemist, which counterfactual makes sense to me to use, or like in a real life application? So those are the things that you have to be mindful about. And the next parameter is the size of the chemical space. Well, of course, when you increase the sample space, the size of your chemical space, you will have more and more molecules which are similar. Like by similarity here, I have considered if a molecule has a time order similarity greater than 0.7, then I have considered it similar in this example. But of course, when you expand your chemical space, it's like when the chemical size increases, you are moving, like, let's say this is like moving closer and closer to capturing the entirety of your chemical space, hypothetically. But of course, it saturates when you reach, like when you move, grow and grow your chemical space. But one of the limiting factors here when you're working with the MMACE algorithm is that when you have a greater sample space, of course, it will be limiting your computational speed. So that is the limiting factor here that a user has to be mindful about. And then, right. One of the limitations with the stoned algorithm, however, is that, yes, it generates valid molecules via mutations, because but the problem is it doesn't have any information about the chemical stability or the synthesizability of the molecule. Now, for this method, for this application to be more used, like to be applied in real life applications, of course, you have to be mindful about the chemical stability of your counterfactuals as well. And yes, we do understand this is a limitation currently. So to address that, we propose an alternative method in place of the stoned algorithm to identify to generate the local chemical space. We suggest querying the PubChem database. So by querying the PubChem database, of course, you can expand the chemical space would be molecules that are purchasable and of course available in the data set. So that is something that we are investigating further as well. But now let me talk a little bit about our exmol package. Now we have our MMACE implementation in our package, and it's a very user-friendly software, and you can install it with just pip install. Dr. White he's the major contributor, so thank you. If you want to take a look at our code, it's available in our website, in our GitHub page repo as well. Now, this is first of all, I use an open source software because we believe in making science accessible to everybody and user friendly, and it has multiple examples, so that even without much knowledge about using the even about our algorithm, you can look at examples and use it. And the software not just allows you to generate counterfactuals, but it allows you to generate nice figures so that it is very, very helpful. Now, I am showing you how, like a very brief demonstration of how to use our software, because as a student, most of the time, I find it extremely beneficial if there's a demonstration. So even if you're not quite familiar with software, I think this would be helpful to somebody who's watching this talk. Right, so first of all, you import the package exmol, and you have to generate the counterfactuals for a given molecule of interest. So you tell this is my smile string, or if you have a self is embedding also, that's fine. And first of all, the first step is generating the sample space around it. And you can do it by this function sample space. So you give your base molecule and your model, whatever the model that you have. Here we are using this wrapper function to say my model takes in smile strings, not selfies. And this flag just indicates that I'm only using one base molecule, not a list of base molecules. Okay, so this function will generate the local space around the given base molecule. And then I want to identify what are the counterfactuals in this space. So to do that, we call this function CF explain and give your sample space into it. Once you have the counterfactuals, you can either plot them like this, or you can even look at the, I'll show it in a little bit. So this is very easy. That's it, to generate the counterfactuals, and then you can use your intuition to generate the explanations for it. Now the chemical space, there are already, either you can change the size of the sample using this number of samples, or there are preset chemical spaces that you can use. For example, medium is the default chemical space, the preset value that we use. It has 1 to 2 molecular mutations, or if you use narrow, you have like only one change. Or you can say, I'm using the chemt method where we query the PubChem dataset instead of just using the stoned algorithm. Also, if you're interested, I think somebody asked this question also in the chat, you can give one of your datasets of interest if you do not want to use the stoned algorithm or the PubChem dataset. Right. Now, I think Emily, somebody asked this question, whether we, how can we identify what is the structure of each data point? And each counterfactual is a Python data class. So you have all the information pertaining to a counterfactual: the smile string, the selfies, the similarity to the base molecule, and the prediction from your model. So you can use this counterfactual to do further analysis as well. Right. In this, this is just once you have the counterfactuals, rather than just printing them in a line, you can also visualize where each counterfactual is in your chemical space. Now, this chemical space is actually plotted for visual purposes. What we have done here is that we take the similarity, the pairwise similarities between each molecule. And so we do a dimensionality reduction on this matrix and projecting it to the first two principal components for the plotting purposes. And again, the Tanimoto distance is measures the similarity between them. And yeah, and always the base molecule would be the furthest point for how this plotting code is done. And yeah, and so the last thing I want to talk about is the future directions. We talked a little bit about this here and there. Yes, the stoned algorithm generates valid molecules, but for real life applications, this might not be enough. We might need to be mindful. We need to have information about the chemical stability or the synthesizability of the molecules. So this is something we are investigating, how to incorporate that knowledge in when we are generating the counterfactuals or expanding the chemical space. Yes, that's one thing that we're interested in. And again, I think, yes, this question also popped up at the very beginning, whether we consider chirality or of the molecules when we are talking about molecular representations. Yes, that's a limitation when we are using molecular fingerprints and tiny motor similarities. Now, to address that, we have to investigate further into how we can overcome such limitations. Like, so yeah, now those are things that we are investigating currently. So yeah, I would like to conclude this talk now, and I would like to thank everybody who's attended here and the organizers for giving me this opportunity, and my lab mates, and especially Dr. White for being a great mentor. And check out our website. All our work is there, and also we have Dr. White's fun chemical projects also listed in it. Yes, and also I think we have some positions open, so come join us. Yeah, thank you. Thank you so much. Let me check if I have any questions. Yeah, thank you. I think Elena has a question. Yeah.
Yes, hello. Sorry, it would be easier for me to speak this one out. Yeah. So with regards to dealing with regression, I have two questions. First, do you choose the delta outside of the experimental measurement range, error range? And then two, particularly for drug-like molecules, say, for example, having a log P less than 5 would be fairly interesting. Do you sample closer to that range and care more about molecules that cross into, say, more drug-like or, unsoluble in water, rather than looking at small changes at the range of log P, saying, moving from 14 to 12? And should those be given more weight?
Yes, actually, in our paper, in our work, we didn't like put so much focus into different applications, like how that, the importance of the magnitude per se. But what I wanted to show here was that, of course, this is user specific. Like, if you are interested in a magnitude of larger than 5, yes, that can be done as well. But in this work, we only used a value of 1 because we just wanted to demonstrate this is how you tackle with a regression task. Does that answer your question?
Yes, thank you.
And we have another question, Dominique.
Hello, thank you for your great talk. One question I have regarding the explainability is that there exist other methods that look directly at, for example, what the model uses to do the prediction. For example, if you use a random forest, you can then check the importance of the features, or if you use a GNN, you can look at the gradient. And my question is, like, how does this compare? How does this explainability compare to these other types of methods that look directly at the model itself? And which method do you think makes more sense from a chemistry and biochemistry point of view?
Well, I cannot answer which method is better, because I would say all methods are important. So it depends on the specific application, I would say. Now, if you take a look at Shapley values, it would tell you which features contribute most to a given prediction. But counterfactuals, I think I find it easier because it's very intuitive, and you can just look at it and come to a conclusion. But especially if you have feature maps, it might not just be interpretable to a user who is not very familiar with machine learning. So I think it comes with your expertise, or what you would prefer, rather than generalizing. So always you have to find that balance between which method would be more interpretable, or with more understandable, or more accurate, So I think we have to find the balance between those.
And do you think we could combine both approaches, for example, using the feature maps to decide where to mutate the molecules instead of doing a mutation? Like,
I'm not sure how you select the mutation there, but like using the feature maps, you can find which regions are important to the model and mutate these regions specifically to get a more accurate feeling of what's going on.
Yes, actually, Heath, I think she's here today. She's working on that specific project right now, combining this with, I think it was the Lime method. Yeah, Heath can answer that. I think she's here in the audience. Heath?
Yeah, hi. So yes, I am working on that. I like the point that you made where we can mutate that specific region. That's not something I've gotten to yet, but that's something definitely we can consider in the future.
Yeah, thank you for your answers.
Thank you. Are there any more questions? I can't see.
I have one question maybe.
Yes.
So a counterfactual seems like well, I'm pretty sure it's a causal concept, right? I've personally gotten kind of into the whole concept of causality through the work of Judea Pearl, among others. And in that line of work, I think the argument that kind of is at the center of it is that we cannot expect to discover causal relationships without having a model of the underlying data generation process. Did you consider this work when you did you kind of consider this other line of work by Pearl and all his associates and other professors while working on this project, and how do the two relate?
We do have ongoing projects that we are looking at that work. I think Dr. White would know exactly what to say, and I don't know what not to say about that.
Yeah, I think I'll just say that a lot of this work is grounded in philosophy, and in philosophy, there's a categorization of explainability. Mm-hmm. And in that categorization, counterfactuals is a broad category, and one subset of counterfactual explanations is causality. And so causality is a narrower concept than counterfactuals. And in fact, there are some contrived examples of things which have a counterfactual explanation, but no causal explanation. But that's philosophy. I think as soon as you start putting these things into, or connecting with machine learning or mathematics, then I think you can show an equivalence between counterfactuals and causality. And just a reminder that Pearl's work is one system of causality. There are other systems as well. But to your specific question about the connection of causality in the data generation process, I am not sure how, or I guess I'm not, I guess it depends on if you think your explanation is about the underlying physics that you're trying to capture with your machine learning model, or if you're just interested in explaining your machine learning model. Because if you're just explaining your machine learning model, then data generation process is enumerating chemical space. But yeah, I understand that if you're trying to get like a causal model of blood-brain permeation, then you run into a lot of problems if your model actually captured the mechanism. And if so, then yes, perhaps you can explain the causal mechanism, but maybe your machine learning model is just counting the number of, oxygens. And so then it's nothing to do with the reality.
Yeah, no, that makes a lot of sense. Thank you. Thank you for the answer.
Yeah, sorry, I have a lot to say about this topic, so.
Please do.
One more question for Geemi. I was wondering if you guys have tested, maybe asked some chemists to review some of the counterfactual that you have discovered and give their opinion on whether like this actually explain the activity or the inactivity of the molecule. And second question is, seems to me like when I see those work in explainable molecular modeling is that we actually need a benchmark for those type of methods, like a benchmark that actually say, okay, for this molecule, this is what we should change to change the activity, like that might be given by chemists, and seems that this is lacking. Are you aware of any group and people working to bring such benchmark to life?
First, to answer the first question, I mean, we are the chemists in who, generate the explanations, but not somebody outside. I think we trusted our judgment that we are able to make that explanation. And for the second question, you were asking if there is a benchmark for counterfactual explanations. Was that correct?
Yeah, for counterfactual or just explainable AI in general and molecular modeling in general.
I'm not sure. Dr. White, do you know something along those lines?
I can't remember the name of the group, but there is one on GitHub of a benchmark of feature attribution and activity cliff modeling. But that's just one specific kind of explainable topics. But I mean, what you're getting at is something that is a big problem, because there's a way to approach this from philosophy or causality, but then there's a way to approach this from like human-computer interaction, and that like the definition of a good explanation is if somebody can understand it. Then there's actionable, like the definition of a good explanation is if you can actually act on it. So this is what you're getting at, is a question which is not just a chemistry question, but an XAI question that I don't think has been resolved yet. But people are working on it. It's a good question.
Thank you. Cool. Thank you.
Thank you.